But let me set up a set of coordinate axes here. X-axis, y-axis, and we'll only focus in two space because it's one of those things that, I mean, in linear algebra, it kind of works out this way very frequently, where if you understand something in one space, it transcends to others. So you like understand everything there is to know about two space, and as far as matrix operations are concerned, and three space kind of works itself out. Same thing with four space. So we have some things, some values for vectors known as unit vectors. I'm just going to draw an arrow here to this location at the coordinate of 1, 0. All right, that vector is I. Then coordinate going to 0, 1, that vector is known as J. All right, so I is the vector 1, 0. Or if you want, you might be more familiar with it this way. If you studied vectors in other courses, the triangular brackets are probably the notation that you use. J01. Put those two vectors together, you get the IJ matrix. First the I, 1, 0, then the J, also known as the identity matrix. This forms a basis for all of two space. I've used the term basis pretty frequently. We're actually going to, later on in the course, learn how to change our bases. But for now, I mean, you can just think of it as like the scale that you're using in whatever dimensions or subdimensions you're working with, right? So, I mean, you think about the real number system. Going by whole numbers gets the job done frequently, but not always, right? Sometimes you want to go with real numbers because that allows you to introduce fractions, decimals, and things like that, right? So these values form the basis for the entire two-dimensional plane. And we know this because these columns actually span two space. All right, if you think about the process we use to find span, it really is just reduce row echelon form and see what you come up with. Right? You get a solution, and it doesn't matter what the solution is, it just has to exist. We get a solution for x and y for every location throughout two-dimension space. Okay? So it forms a basis, just like, I don't know, millimeters could form the basis of I don't want to say the metric system because that's not. I guess, yeah, probably. Because if you operate on a millimeter, you can get to any other. Well, but I suppose that means you can let meters form the basis for a metric system or centimeters or whatever. Because just basically through multiplication, one form of units could become any other kind of form of units. All right. So here, I mean, you say, well, what about fractions and decimals? Well, yeah, I just have to multiply by a fraction or decimal, and I'll get a fraction or decimal. Negative numbers multiply by a negative. Right? So this identity matrix allows any vector to maintain its identity. Right? So for example, take the vector 2, 1. Through matrix multiplication, we would get 2 multiplied by 1, 0, plus 1 multiplied by 0, 1. All right. So 2, 0 plus 0, 1, result 2, 1. Right. So, cool. We know how to maintain the identity of some vector. What if I want to change its identity? What if I want to make it the exact opposite? What if I want to do a reflection or a rotation or something like that? Well, there's 2 ways to handle it. One would be to make an educated guess, which is actually how I made my way through. You're like, all right, I need something to become negative. So make that negative. Did it work out? No, it's not quite what I want. Make that one. Okay, there we go. We're good. Okay, so, okay, we don't want to do that. Decide on what, well, you're not really deciding, you're being told, but you have some sort of operation, some sort of transformation that you need to conduct. So instead of conducting it on this actual matrix, you know, like negate this, swap those things, I don't know, like you could do that, I guess, but instead, take a look at your basis vectors, because again, if your basis vectors form the basis of every ordered pair in real space, then whatever happens to I and j would then have to happen to everything else. So let's say, for example, that I want to do well, I'm not going to give it all away right away. I'll just say a reflection to 1 over the y-axis. All right, so forget about 2, 1 for now. Let's just deal with I and j. Because again, and this is something to keep it in mind, because it's the foundation of transformations, and it'll allow you to understand the concept. Like you see the table above, it's got like, well, if you want to do this, use this matrix. If you want to do that, do that. Okay, fine, write it down if you want, but it's not true understanding. Okay, so I'm going to plot I and j. All right. So I want to reflect over the y-axis. Well, my j vector is on the y-axis. That wouldn't go anywhere, right? So I mean, if it were floating somewhere else, if it were kind of shooting off into the first quadrant, fine, it would have to move. But since it's already on the y-axis, it's not going to move. If I want to reflect the I, though, it's going to go in the opposite direction. All right, so I'm going to take my I and kick it over in this direction. All right, so it's not I anymore, it's negative I. All right. If you don't like the I and j notation, that's fine. Just work with the unit vectors. And by the way, they're called unit vectors because they have a magnitude of 1. All right, that's something important to think about, because if you're wondering, oh, well, any of my former students have to be wondering, is the unit circle going to work its way into this course? You're damn right it is. So magnitude equal to 1, that's a big deal. Anyway, so I becomes negative I. That's great. But really more importantly, 1, 0 becomes negative 1, 0. my j vector is still at coordinate 0, 1. So my transformation matrix would be negative 1, 0, 0, 1. Vectors for I, or the vector for I, followed by the vector for j. So then we'll test it out. We'll take that, multiply it by 2, 1, and see if it actually gives us, I mean, it's not your first rodeo when it comes to transformations. You know to reflect something over the y-axis, all you're doing is negating the x value. Okay, so we're expecting negative 2, 1 as our final answer. So let's see if that happens. Ah, I almost made it a fraction. I almost actually got through the whole thing without trying to make this into a fraction. Okay, so negative 2, 1 would be the transformed vector. So 2, 1, which is shooting off in this direction, would then be shooting off in that direction. All right. But what if you needed to do a rotation? I don't know, something like a, we'll say a 60-degree rotation counterclockwise. So again, we have I and j. And I said it before, but I'll say it again. You don't have to call them I and j if you don't want to. You just need to know that it's going to be a 1, 0, 0, 1. Okay? So I want to rotate these 60 degrees in the counterclockwise direction. So that'll work. So I is going to be shooting off somewhere over here. And j, another 60 degrees, somewhere down here. All right, so again, it's a unit vector because its magnitude is equal to 1. I have a 60-degree movement around a circle whose radius is equal to 1. Students are never as excited about this moment as I am, but whatever. If you're moving 60 degrees around a circle whose radius is equal to 1, you're moving 60 degrees around the unit circle. The coordinates in your unit circle, x comma y, cosine of the angle, comma the sine of the angle. Okay? So I know, regardless of whether or not I actually know my unit circle stuff, I do know that this has got to be cosine of 60, comma sine of 60. The big question is, do you actually know what the cosine of 60 is and what the sine of 60 is? That would be great. It's not the end of the world if you don't. If you're just, when I do give you a unit circle quiz late next week, it might be not your fondest memory of the course, but it'll be okay. So anyway, I'm moving this vector 60 degrees beyond 90. So now I'm at 150. So for my transformation vector, which was 1, 0, 0, 1, our new I would be cosine 60 sine 60. Our new J would be cosine 150 sine 150. All right. The cosine of 60, if you please. 1/2. Sine of 60. Rad 3 over 2. Cosine 150. Negative root 3 over 2. And the sine of 150. Calculator can bail you out if you don't know them. Because, you know, even the root 3 over 2 ones. So, just do, let me make sure I'm in the right mode. No, there's no requirement that you're in radian or degree mode as long as you just know what mode you're in. Because you don't want to type in cosine of 60 when you're in radian mode. So that one, nice, right? Gives you a 0.5. Sine of 60. Hideous decimal. Math frac would be great, except it's not going to work. There's no math rad key. But what we can do is, well, we assume that this is the square root of something, right? So square it. 0.75 is 3/4. So I know my answer is the square root of 3/4. So I just have to simplify that, which is rad 3 over 2. All right, so if you don't know your unit circle stuff, you can make do with this. If you don't know your unit circle stuff and you look at what I just did there and you're like, oh, that seems way too complicated, I'm not doing it. My answer has always been and will always be, you can't have it both ways. You can't not know the unit circle stuff and then turn around and scoff at the one bailout that you would have, the calculator approach. Right? So if you're not going to make the time to know the unit circle, then know this, right? Because it's one or the other. I mean, unless you're okay just throwing away points on the test. So again, just to recap, you put it in whatever the angle is. Make sure you're in the right mode. We know it's a funky decimal. You know it's the square root of something. So square it and see what you get. Okay? It should end up being a clean decimal. If it's a clean decimal but not recognizable, then hit math frac. It'll kick it over to the fraction form for you. And just pop a root over it. And if you can simplify it, simplify it. So this one would be radical of 3 over 4. So keep the radical on top. Root 4 becomes 2. All right. So you can finagle it. The other option would be to actually carry out the multiplication using your cosines and sines and just kind of hope it all comes out in the wash. I wouldn't have high hopes for that though. Anyway, so to actually carry out the transformation, we're multiplying by vector 2, 1. So this plus this. All right, so 1 root 3 plus negative root 3 over 2, 1/2, not ideal, honestly, I think it was probably better off leaving it in unsimplified form because at least that way I'd have a common denominator. So this is 2 over 2 minus root 3 over 2, so 2 minus root 3 over 2. And then 2 root 3 over 2 plus 1, so 2 root 3 plus 1 over 2 is what that's equivalent to. All right, so, yeah. I mean, maybe there's a way to finagle a, calculator approach to get you these answers. I don't know what it is. I mean, my little trick of saying, oh, it's a funky decimal, just square it. That only works if it's a simple ratio. Something like this. If it's a sum or difference, all bets are off. All right, so. But that shockingly is what the transform coordinates would be. Very exciting.